So what we have is we have a triangle. The only requirement is that the base angles here are acute. And what we want to do is we want to somehow or other draw a square. So I'm just going to roughly sketch it out. In this case, we can see that we have a rectangle that is slightly wider than it is high. So how can we get a square into this triangle using just a compass and straight edge that lies on this base and then touches the two sides? As mathematicians, before we start on actually constructing something, a good question to ask is, does this exist? How do we know we can get exactly a square instead of just a rectangle? So what we're going to do is actually use this idea of rectangles. So as mathematicians, sometimes we're looking for squares, but we can't find a square. So we relax the restriction and we start looking for rectangles. And then we hope we can find a rectangle where the height is equal to the base length, and then we know we have a square. So how can we get rectangles? Well, from the height of this triangle, we can just draw any parallel line to the base, and then drop the perpendiculars, and we now get a rectangle. We see that this blue rectangle is now a lot higher than it is long. The green rectangle was a lot longer than it is high. So we hope that there's a square that lies somewhere in between this range.
As you sort of slide between the two.
Right. So let's actually draw that out, what that looks like. So I'm going to draw a graph. Firstly, I'm using a ruler to measure stuff. So this isn't yet a purely straight edge and compass construction. So we're going to plot the height of the rectangles as they get lower and lower. So for now, I'm going to use my ruler to draw that out. So it is of about 4 units. So over here is going to be about 4 units. And at a height of 0, the height of the rectangle is 0. So what we have is a straight line here representing the height of the rectangle. So now that we have the height of the rectangle, we're going to draw the width of the rectangle. When the height is at the full height, the width of the rectangle is 0. So we have a point down here. And when the height is at 0, we have the full length of the base, which means we're going to have a straight line here. And what happens at this point of intersection? Well, at this point of intersection, we know that the height of the rectangle is equal to the width of the rectangle, and so that gives us a square.
So we can do a square.
So we can do a square, and when we had the use of this ruler to transfer heights and lengths around, we could find this is the height at which the square will occur. So if we have a proper construction, the hope is that we can draw a square here.
Oh yeah.
So we'll see if we actually can match that. Another trick that mathematicians use is that if they can't find a square, they actually force out a square. So how do I force out a square here? Is that it's hard to force a square in there, but I can draw a square down below. So using my compass and straight edge, I can actually draw out a square. And we're going to use this to approximate a compass. So over here, we want to draw a square. It's going to come down to here. Over here, we want to draw a square. It's going to come down to about here. And so this gives us an approximate square. And actually, I do not need this ruler anymore, so I'm going to put it away and just use a straight edge. So we are going to continue this out and continue this out. And now what we have here is we have a square in this large triangle. So it's not quite the square that we want in this small triangle up here, but at least it's a square in a large triangle. What can we say about this small triangle and this large triangle? Because this edge moved down parallel, these two triangles are actually similar. So there is a mapping that brings us from this small triangle to this large triangle, and we can ask, what does the mapping do to this square?
Because you've got the square now.
Yes. So think about what happens to the base of this square as we expand the small triangle to the big triangle and as we contract it back. This base is actually just going to be a straight line through to the vertex of the original triangle. Likewise, over here, if we connect the vertex to this point, is how this point will move as we contract the triangle. So now the base of the large square goes over to these 2 points. And what that means is that we now have the base of a smaller square in this triangle up here. We just need to construct the perpendiculars, and this will give us our square.
Got it.
And as I mentioned earlier, we can compare it to this diagram on the right, and we can see that we are reasonably close to what the calculated answer is. Method 1, where we constructed the 2 lines that intersected each other to find the height of the square. And method 2, where we forced a square to get into this triangle. So now we're going to look at a third way. How else can we relax the restriction of the square? Instead of forcing all the vertex to line up perfectly on the edge of the triangle, maybe we could say, hey, let's just have the base of the square touching one side of the triangle. Okay, we can also continue drawing more squares and see what they look like. Okay, and so this figure of squares that are touching the side of this triangle, we hope we eventually will get to a square that does indeed touch this side of the triangle. If we can find such a point, we are done. And what we have here is that we again have our similar triangles. So we started out with this triangle, and we moved the base over, we got to this triangle. So what then does that tell us about these points and the vertex of this triangle? Is that these 3 points will form a straight line. So we could connect up these 3 points and see where it intersects the other side of the triangle. And then from here we know if we drop the perpendicular and we drop the parallel line, that will give us a square.
Ah, that's almost simpler than the other one.
That is indeed simpler than the other one. And both of these use the same idea of similarity. All right, so we're back on the first diagram. And remember, what we wanted to do is start off by constructing a square. So I'm going to just quickly measure off and we said that the vertex of the triangle and this corner of our now relaxed square, we want to extend this line, and we can see that, hey, it does go through this other point on a triangle. That's pretty amazing.
Look how happy you look. You're very happy with yourself.
So we have 3 different methods here, and they all agree on this one point to give us the square. We drop the perpendicular, we drop the parallel line, and we form our square in this triangle.
Get wild. Ooh. So it looks like for any triangle, we will have those 3 segments intersecting in a point. Well, that point turns out to be the center of mass, or our point, which also is known as centroid,